Bridges are more than just structures. They are lifelines. They connect communities. They facilitate trade and travel. Bridges represent the ingenuity of humankind. They stand as testaments to our ability to overcome physical obstacles. Imagine a world without bridges. Transportation would be difficult, economies would suffer, our lives would be vastly different. Bridges are essential to our modern world. They are marvels of engineering and design. They require careful planning and construction, from small footbridges to massive suspension bridges. Each bridge serves a vital purpose. Each plays a crucial role in our interconnected world. Throughout history, bridges have sometimes failed. These failures, though tragic, have served as critical learning points for engineers and designers around the world. They remind us of the importance of meticulous planning, precise calculations, and the need to anticipate the unpredictable forces of nature. These failures are stark reminders of the importance of careful engineering. Every blueprint, every calculation, and every material choice plays a crucial role in ensuring the safety and longevity of these structures. Engineers must consider not only the immediate environment but also potential future changes and stresses. They highlight the unforgiving nature of physics and the environment. Natural forces such as wind, water, and seismic activity can exert tremendous pressure on bridges, testing their limits and revealing any weaknesses in their design or construction. Bridge collapses can be devastating events. The immediate aftermath often involves rescue operations, emergency responses, and a thorough investigation to determine the cause of the failure. These incidents can disrupt communities, economies, and lives. They can result in loss of life and significant damage. The human and economic toll can be immense, with families affected, businesses disrupted, and infrastructure needing extensive repairs or complete rebuilding. These events often lead to investigations and changes in engineering practices. Each collapse is meticulously studied to understand what went wrong, leading to new standards, improved materials, and innovative design techniques aimed at preventing future failures. One of the most infamous bridge collapses is the Tacoma Narrows Bridge disaster in 1940. Known as Galloping Gertie, this bridge's dramatic failure was a wake-up call for engineers and designers worldwide. This event, captured on film, showed the bridge twisting violently in the wind before collapsing. The footage became iconic, illustrating the destructive power of aeroelastic flutter and the need for aerodynamic stability in bridge design. This highlighted the powerful forces of nature and the need for designs that can withstand them. Engineers learned valuable lessons about the importance of considering aerodynamic effects and the dynamic interactions between structures and their environments. Studying these failures helps us learn and improve. By analyzing past mistakes, engineers can develop better, safer, and more resilient structures. Educational institutions incorporate these case studies into their curricula, ensuring that future engineers are well-versed in the lessons of the past. Each collapse provides valuable lessons for future bridge design and construction. The knowledge gained from these events drives innovation and progress, leading to bridges that are not only functional but also capable of withstanding the test of time and nature's challenges. Metal fatigue is a significant factor in bridge collapses. This phenomenon occurs when metal structures are subjected to repeated stress and strain over time. The constant load-bearing and environmental factors contribute to the gradual weakening of the metal. Bridges are subjected to constant stress from traffic, wind, and their own weight. Every vehicle that crosses, every gust of wind, and even the bridge's own weight contribute to the stress experienced by the structure. This relentless pressure can have a cumulative effect. Over time, this stress can cause microscopic cracks to form in the metal components. These tiny fissures are often invisible to the naked eye but can be detected with specialized equipment. The initial formation of these cracks is a critical warning sign. These cracks may seem insignificant at first. However, they represent the beginning of a potentially dangerous process. If left unchecked, these small imperfections can evolve into major structural issues, but they can grow larger with repeated stress. Each cycle of stress and relaxation causes the cracks to expand incrementally. Over time, these cracks can become significant fractures that compromise the integrity of the entire structure. Eventually, the weakened metal can no longer support the load. When the metal's strength is sufficiently reduced, it can lead to a sudden and catastrophic failure. This is often the point at which a bridge collapse becomes inevitable. This can lead to a sudden and catastrophic failure. The collapse of a bridge is not just a structural failure but a human tragedy, often resulting in loss of life and significant economic impact. Inspecting bridges for metal fatigue is crucial. Regular inspections allow engineers to detect early signs of fatigue before they become critical. This proactive approach is essential for maintaining the safety and functionality of the bridge. Regular maintenance and inspections can help identify these cracks early on. By catching these issues in their infancy, engineers can take corrective actions to prevent further deterioration. This allows engineers to repair or reinforce the structure before a collapse occurs. Reinforcement techniques can include welding, bolting, or even replacing compromised sections of the bridge. Detecting and addressing metal fatigue is a constant battle in bridge maintenance. Engineers must stay vigilant and use the latest technology to monitor the health of these critical structures. It is vital for ensuring the longevity and safety of these structures. A well-maintained bridge not only supports the flow of traffic but also stands as a testament to engineering excellence and public safety. Even small design flaws can have major consequences. A bridge's design is incredibly complex. It involves intricate calculations and considerations of various factors. A small miscalculation or oversight can weaken the entire structure. This can make it vulnerable to collapse. One common design flaw is inadequate support for the bridge's weight. If the supports are not strong enough or are positioned incorrectly, they can buckle or collapse under the strain. This emphasizes the need for rigorous design reviews and quality control throughout the construction process. Every detail matters when it comes to bridge engineering. Section 5. Nature's Fury, the Unpredictable Force. Nature can be a powerful force, capable of unleashing tremendous forces on structures like bridges. Earthquakes, hurricanes, and even strong winds can put immense stress on bridges. These events can cause unexpected movements and vibrations. This can lead to instability and collapse. The design of a bridge must account for these environmental factors. Engineers use sophisticated models and simulations to predict how a bridge will behave during extreme weather events. This helps create structures that can withstand nature's fury. Despite these precautions, nature can still surprise us. It's a constant challenge to design and build bridges that can endure unpredictable events. Section 6. Tacoma Narrows Bridge, a lesson in resonance. The Tacoma Narrows Bridge collapse is a prime example of how a phenomenon called resonance can lead to catastrophic failure. Resonance occurs when an object is subjected to a frequency of vibration that matches its natural frequency. This can cause the vibrations to amplify dramatically, leading to violent swaying and even collapse. In the case of the Tacoma Narrows Bridge, the wind created vibrations that matched the bridge's natural frequency. This caused the bridge to sway back and forth with increasing amplitude. Eventually, the stress became too great, and the bridge twisted and collapsed. The Tacoma Narrows Bridge disaster highlighted the importance of understanding and accounting for resonance in bridge design. Section 7. Silver Bridge. Collapse. A case of material fatigue. The Silver Bridge collapse in 1967 is a tragic example of how material fatigue can lead to sudden bridge failure. This catastrophic event shocked the nation and highlighted the vulnerabilities in our infrastructure. The Silver Bridge, a chain suspension bridge, collapsed during rush hour. It was a busy time with many vehicles on the bridge, making the disaster even more devastating. This sent dozens of cars plunging into the icy Ohio River. The scene was chaotic, with rescue operations scrambling to save lives amidst the wreckage. The collapse was attributed to the failure of a single eye-bar in the bridge's suspension chain. This critical component had a hidden flaw that went unnoticed. This eye-bar had a small defect that had been overlooked during inspection. Engineers later discovered that this tiny imperfection had been growing over time. Over time, the defect grew larger due to stress and fatigue. The constant load and environmental factors contributed to the weakening of the metal. Eventually, it reached a critical point and snapped. The sudden failure of this eye-bar was catastrophic. This caused a chain reaction that brought down the entire bridge. The interconnected nature of the bridge's components meant that the failure of one part led to the collapse of the whole structure. The Silver Bridge collapse underscored the need for thorough inspections and the importance of understanding how even minor defects can have devastating consequences. This tragedy led to significant changes in bridge inspection protocols and raised awareness about the critical nature of infrastructure maintenance. Section 8. Lessons learned. Building safer bridges. Bridge collapses are tragic events, but they provide invaluable lessons that help us build safer structures in the future. Each collapse has led to advancements in bridge engineering. We have learned to better understand the forces at play. We have developed new materials and construction techniques. Today, bridges are designed with greater redundancy. This means that if one element fails, others are in place to prevent a complete collapse. Innovations in material science have led to the use of stronger and more durable materials. Computer modeling allows engineers to test designs virtually before construction. This helps identify potential weaknesses early on. Section 9. The Future of Bridges, Innovation and Resilience. The future of bridge engineering is filled with exciting possibilities. Researchers are exploring the use of new materials. These include self-healing concrete and advanced composites. These materials could dramatically extend the lifespan of bridges. They could also reduce maintenance needs. Advanced sensors and monitoring systems are being developed to provide real-time data on a bridge's condition. This will allow for early detection of potential problems. By embracing innovation and incorporating the lessons learned from past failures, we can continue to connect our world with safe and resilient bridges.